Fundamental Theorem of Calculus is taught in countless high schools and universities as the cornerstone of calculus. However, despite being so important, students sometimes miss out on the understanding of why the fundamental theorem works, leaving them unsatisfied. This video is meant to fill in that gap by giving some reason and intuition for the fundamental theorem of calculus. Note that this will not be a rigorous proof, but rather a simple explanation of the theorem. With that in mind, let's get started. Suppose we want to find the area under the curve of a function f of t from t equals a to t equals b. The function f of t is graphed in black over here, and the orange represents the area under that curve from t equals a to t equals b. The purple lines at the ends of the area explicitly show where t equals a and t equals b lie. However, before we can tackle this problem of area, let's first lay out some definitions. What we want to do over the course of this video is we want to find the integral from a to b of f of t dt. In order to do this, let's define a function a of x such that a of x is equal to the integral from a to x of f of t dt. If you are unfamiliar with integrals, know that the top integral, the integral from a to b of f of t dt, simply represents the area under the curve of f of t from t equals a to t equals b. And the second integral for the definition of a of x represents the area under the curve of f of t from t equals a to t equals x. Here's a graph that might give us a little bit of a better idea of what the function a of x is really doing. What a of x does is it finds the area in blue over here. Notice that as I change the value on the slider here, the area in blue changes. What the function a of x does is that for every value on the slider, it finds another value that represents the area in blue. For example, if say I stop the slider at say 2.36, the function a of x would give me the area in blue for the x value of 2.36. Now that we've gotten a little bit of a feel for our a of x, observe what happens if we take its derivative. We get dA dx is equal to ddx of the integral from a to x of the function f of t. For a refresher, a derivative is simply the instantaneous rate of change of a function, and in this case, we are finding the instantaneous rate of change of a of x. This can be found by observing the ratio between an infinitesimal increase in x, which we call dx, and the corresponding change in a of x, which we call dA. Let's look at a graph again to make this more clear. The green area that I've depicted now is the area that is added to the function a of x when x is increased by a small amount, dx. Notice that as I value the value of x for the function a of x, I get different amounts of green area. We're going to call this green area dA. It turns out that dA can be approximated by drawing a rectangle around this green area. Let me draw that rectangle in right now. At the place that I've stopped my cursor, this little rectangle that approximates dA appears to be a little bit larger than dA is in reality. However, if we let the change in x approach 0 so that it really becomes an infinitesimal change, then the rectangle I have drawn becomes a better and better approximation of dA. At the extreme, where dA is approximately 0, the rectangle will basically become exactly the value of dA. Since dA is equal to the area of the rectangle that I've drawn to approximate it as dx approaches 0, it'll be very important to find the area of this rectangle so that we can find dA. So what is the area of the rectangle? Well, let's look at this picture right here. The height of this rectangle is at the point x comma f of x. So its height is f of x. And its width? Well, its width is just dx. Thus, its area is simply f of x times dx. Noting that this is equivalent to dA, we can write the equation that I've drawn on the screen now. Now, if we substitute this equation into our definition for the derivative of a of x, we find that dA dx is equal to f of x times dx divided by dx, and now the dx is cancelled to leave us with just f of x, which is equal to ddx of the integral from a to x of f of t dt by our definition of a of x and dA dx. This part over here is the first part of the fundamental theorem of calculus. At this point, we have all the tools we need to prove the second part of the fundamental theorem of calculus and find a way to find the area under f of t from t equals a to t equals b. Recall that we just said that dA dx is equal to f of x. This implies that capital A of x is equal to some function capital F of x plus c, where capital F of x is a function such that capital F prime of x is equal to little f of x, and c is a constant. You can confirm that this works by taking the derivative of both sides of this equation for a of x, and if you note that the derivative of a constant is simply 0, then this equation will end up being equivalent to the one above. Notice that if we want to find the integral of f of t from t equals a to t equals b, then we can do this by finding capital A of b based on our definition of a of x. However, to do this we must find a value of c so that we can get an exact definition for capital A of x. It is clear that capital A of little a is simply 0 because that is equal to the area under the curve of f of t from t equals a to t equals a, which is an area that has no width. Thus, we can substitute x equals little a into our equation for capital A of x and set that equation equal to 0. Solving for c, we find that c equals negative capital F of little a. Plugging this into our definition for capital A of x, we get that capital A of x is equal to capital F of x minus capital F of little a. Finally, we can find that capital A of b is equal to capital F of b minus capital F of a. And this is equal to the integral which we wish to solve. That last equation at the bottom is the second part of the fundamental theorem of calculus. And with that, we have accomplished our goal. Hopefully over the course of this video you gained a better and more satisfactory understanding of the fundamental theorem of calculus. I will be looking forward to see you in the next video. Until then, goodbye, and as always, thanks for watching.